So I'm Carl Westoby. I'm architect with the QEC focus at New Quantum, as previously mentioned. In case missed it from earlier, New Quantum is a networking provider. We integrate and take photons out of QPUs. We bring them together. We project them into Bell states, and then we use that to generate much larger computational substrates, entanglement fabrics, if you will, than you can build within any particular QPU size. And we, think this is really useful for building fault tolerant, especially early and mid-scale fault tolerant quantum computers, and it's a really enabling technology. So we've done a bit of work, sort of prototyping this out, and we think there are a lot of interesting ways in which you can sort of put all this together. I hope it's inspirational. So this is error correction over an entanglement fabric, and what we start with is a family of surface codes, but not the surface code as you know it. Our surface is not a plane. It's a closed hyperbolic tiling. This sort of, if you imagine taking a plane, turning it into a straw, the straw now has, one hole or two, if you want to count it like that. These surfaces have hundreds of holes. But when you look at it closely, they're little patches, little planar patches. So they work well in a QPU, but when you stitch them together with remote entanglement links with this entanglement fabric, you generate this sort of highly complex topology that enables and really supports more efficient quantum error correction. So we start with a hyperbolic Floquet code, and you can choose the number of logical qubits by tuning this. We fine-grain it by inserting more planar patches, and this lets you increase the distance in a really scalable way. And then we partition that code into multiple different parts for each QPU and stitch them together with the remote Bell states we prepare optically. And all of this delocalizes the error correction across all the processors, meaning you aren't restricted by the size of a processor in terms of which error correction code you want to choose. So just to put a bit of detail on the how to do code remotely, these hyperbolic Floquet codes, I've talked about hyperbolic, now time for Floquet. A Floquet code is a dynamic error correction code, and one of the interesting properties they have is their pair measurement. The checks you do only connect 2 qubits, and when you create a Bell state, that's an entangled state over 2 qubits, so you can directly use it to perform one of these checks. And this means that there's sort of no difference in complexity between doing a local check, where you do it with a 2-qubit gate, and a remote check, where you do it with a shared Bell pair. It's all very uniform, and so if you want to do a local check, you do it with 2-qubit gate and a measurement. If you want to do a remote check, you generate a Bell pair by, as we see on the right, generating photons from 2 separate processors, sending them through the routing layer, bring them together as a Bell state, analyzer, and projecting that into a Bell state, and then doing 2-qubit gates and measuring out that Bell state. And one of the things we wanted to look at is, does this sort of impact the feasibility of error correction? It might be true that you really want to do it locally because the thresholds are much better. And we actually find that the thresholds are much kinder to us remotely. Sort of for some work from the early part of this year, we looked at doing this sort of in a circuit noise model, sort of looking vaguely at an ion trap-like noise model. And we're looking at about a 10 times softer, easier error correction threshold for the remote gates as for the local ones. And there's a slight boost in complexity on a remote gate, so we think that's pretty comparable, and pretty well supports this idea of there being no particular harm in extending your code outside of the node and really getting access to these much greater distances and and along with greater distances, much greater flexibility in choosing the complexity of the code and the number of logical qubits you can encode within that code. Just sort of to bring all that together, what we really feel is this is a flexible way of choosing how to build a system. The distance as opposed to any monolithic machine or where you're trying to error correct locally, you can choose a code that is not bound by the size of a particular QPU, a particular set of qubits you have locally. You can choose whatever you want to meet the logical fidelity and so gate depth requirements you have for a particular algorithm. Equally, the rate you can get access to, because we can generate non-planar entanglement links by crossing over the fibers because they are one-dimensional. The encoding rate can be much higher. You can get these denser codes that really approach the sort of metrics we get from good QLPC codes. And sort of when you play both of these things off against each other, because the quantum volume you can see, I mean Sandia quantum volume in this case, you can get for a particular code is really exponential in that distance. Because as you increase the distance, you massively increase the number of gates you can get before failure. You can really push your logical fidelity and get access to sort of small, compact but very deep circuits that we see as sort of these very natural early fault tolerant utility targets. And perhaps compared to some other approaches to networking, because we've shared the cost of compensating for all errors within the same code, we don't pay the cost of correcting those fault-tolerant links in a sort of separate stage. A good fault-tolerant code is a good fault-tolerant code, and only paying that cost once really improves your overheads. Thank you.